You know, in the world of modern software, where our phones and computers are juggling a million things at once, there's this really sneaky and chaotic bug that's always hiding just under the surface. It's the kind of thing that doesn't always pop up, it's a total nightmare to track down, and it can make your program spit out completely random results. What we're talking about is something called a race condition. And today, we're going to break down exactly what that is and why it's such a big deal.
And that analogy, it absolutely nails the problem. A race condition is pretty much that exact scenario playing out, but with bits and bytes inside your computer. When you have multiple parts of your software, we call them threads, all racing to use the very same piece of information, like a number in memory, the final result is just a roll of the dice. It all depends on who gets there a millisecond sooner. It is a perfect recipe for digital chaos.
Okay, so how are we going to tackle this messy topic?
Well, we've got a roadmap. First, we'll define what a race condition actually is, that race for resources. Then, we'll see how it makes code totally unpredictable. After that, we'll dive into the common ways this error shows up. Then, the good part, the solution for bringing order to the chaos. And finally, we'll talk about why these things are so incredibly hard to hunt down and fix.
All right, first up, let's get on the same page. What do we even mean when we talk about a race inside your code? What are these resources they're fighting over?
So here's the textbook definition, but let's break it down. It's all about that simultaneous access. You have two or more threads, and they both need to read and change the same piece of data. Because your operating system can swap between these threads at any given nanosecond, you have zero guarantees about which one goes first. Basically, the final result is a total lottery, and it all depends on the random timing of who does what, when.
And this is a super important idea right here. This bug doesn't just happen anywhere. It happens in a very specific place. We call that the critical section. It's that exact chunk of your code where the shared resource is being touched. Think of it as the battlefield. It's that one single page in the notebook where everyone is trying to scribble at the same time. Okay, theory is great and all, but what does this mess actually look like in the real world? Let's move on and see how this abstract idea creates some very real, very unpredictable problems when you're actually writing code.
Whoa, okay, look at this. This just lays it all out, plain and simple. On the left, you've got a basic loop. It adds 1 to a counter 100 times. The result? It's always 100. Every single time. Rock solid. But look at the right. We add one little instruction to run this code in parallel using multiple threads. And boom, the result is, well, it's a mess. You might get 95, maybe 87, maybe some other number. And it could be different every single time you run it. So what is going on here?
So why? Why does it break? And this is the absolute key. We look at something like count++, and we think of it as one single action. It happens instantly, right? Wrong. To the computer, it's actually 3 distinct steps. First, it has to read the current value of count. Then, it has to modify it by adding 1, and finally, it has to write that new value back. The race condition happens in the tiny, invisible gaps between those 3 steps.
You know that whole read, modify, write sequence we just talked about? That's a classic way these bugs pop up. But it's not the only one. Let's take a look at the most common patterns for how these failures actually happen in the wild.
So you've got 2 main troublemakers here. The first is check, then act. This is when your code checks if something is true, and then, based on that check, it does something. The problem is, another thread can swoop in and change the situation after you've checked, but before you've acted. And the second one is read, modify, write, which is exactly the disaster we saw with our counterexample.
Let's paint a picture of this check then act problem. So thread A checks a value x and sees that it's 5. Great. It gets ready to do something based on that fact. But bam, right at that moment, the operating system decides, nope, your turn is over, thread A, and pauses it. Then thread B gets to run and it changes x to 6. A moment later, thread A wakes back up and continues right where it left off, acting as if x is still 5. It has no idea the world changed from under it, and that leads to a bug.
And here's our old friends, the read, modify, write problem, broken down step by step. Thread 1 reads the value x and sees it's 7. But before it can do anything, thread 2 also reads x, and yep, it's still 7. Now both threads on their own calculate 7 plus 1, and they both get 8. Thread 1 writes 8 back. Then thread 2 writes 8 back. See the problem? We did 2 increments, but the answer is 8, not 9. And poof, a whole increment just disappeared. Gone. Okay, so things are chaotic, right? The problem is a total mess. So obviously the solution has to be about bringing some order to that chaos. How in the world do we stop these threads from stomping all over each other's work?
And that big answer, that key concept, is called synchronization. It's basically a whole collection of programming techniques that developers use to control access to those shared resources. With synchronization, you turn that chaotic 8-lane traffic jam into a nice, orderly single-file line.
And the tool you'll see used most often for this is called a mutex. It stands for mutual exclusion, which is just a fancy way of saying only one at a time. The best way to think about it is like a lock on a door. Before a thread can go into that critical section, it has to grab the lock. While it holds that lock, no other thread can get in. They all have to wait outside. When it's finished, it unlocks the door, and the next thread in line gets its turn.
And, a mutex is just one tool in the toolbox. Developers have a bunch of these things. You'll hear names like critical sections, monitors, semaphores. They all work a little differently, but they're all designed to do that same fundamental job: protect the shared data and bring order to the chaos. So, just use locks, right? Sounds simple. Well, yeah, but that brings us to the really, really frustrating part of all this: actually finding these bugs in the first place.
Man, this quote from a developer just hits the nail on the head. These bugs are so nasty because they aren't consistent. They depend on this incredibly specific, unlucky timing. A bug might only show up once in a million runs, only when the threads align in just the right, disastrous way, and that makes them almost impossible to reproduce on command.
And this is the crazy part. This is the real kicker. The very act of trying to find the bug can make it disappear. When you run your program through a special tool called a debugger, it slows everything down and changes all the timing. That little bit of extra overhead is often just enough to prevent the unlucky timing from happening. So you're just sitting there staring at your screen, pulling your hair out because the bug is gone, but you know it's still lurking in there somewhere.
And if that wasn't enough, there's also performance to worry about. A lot of people think using locks is always slow, but that's not quite true. The reality is a little more complex. When only one thread wants the lock, we call that no contention. It's incredibly fast. We're talking nanoseconds. The massive performance problem comes from contention. That's when a bunch of threads are all trying to get the same lock at the same time. This forces the operating system to do a ton of extra work, and it can grind your whole application to a halt. The real art is protecting your data without creating these traffic jams.
So at the end of the day, this all boils down to one huge question for anyone writing software right now. Think about it. Your phone, your laptop, everything has multiple processor cores these days. Writing parallel code isn't really a choice anymore. The challenge isn't just about making things faster. It's about figuring out how we can do it safely, how we can build our apps to avoid falling into this hidden, unpredictable trap of pure chaos.